So in the last section, we looked at finding volumes of revolution using disks and washers. Today, we're going to take a look at using shells. Now, shells is another method. Sometimes problems can be done either way. Sometimes it's significantly done easier with one of them than the other. Now, for the shell, basically, you're just taking a cylinder and you're adding together the volume of all these cylinders. Well, your thickness here is still your width. And then if you would take a piece of paper and roll it together, it's really, if you take the shell and unroll it, it's a rectangle where your height, and then you got to multiply it by your circumference to be able to get your volume. So if you add together all the cylinders of a shape, you would then have to do your integration. And that's really what we're looking at here. Remember that we are dealing with the volume of a shell or a cylinder, which would be 2 pi times your height. Because if you go ahead and look at a cylinder, your volume would be your height in green times this. Because if you would unroll that, you would end up getting a rectangle where that purple circle on the top is really your length right here. So it's length times height is really all we're dealing with. And so that's what we have down here. We have our 2 pi in front from this here. We have our radius, and then we have our height. Our radius down here is what's in the blue, and then our height right here is what's in the red, or not the red, the green. Can't tell my colors, wow. So that's what we're dealing with here. Now, whether you're dealing with y's or x's, it's really the same thing. So when you're looking at volume of a shell, you go 2 pi. If you're dealing with a vertical axis of revolution, you're dealing with your x's. Oops, sorry about that. If you're dealing with a horizontal axis of revolution, you're dealing with your y's. So it's 2 pi. If you're dealing with your x's, your a and your b would be how far left and right your shape goes. And then your radius is always your variable minus axis of revolution, or if your axis of revolution is over here on the right, your axis of revolution minus your variable. Basically, you just have to do big minus small. So what's underlined in red here is kind of representing your radius. It's either x minus your axis of revolution or axis of revolution minus your x. Then the h is how far up and down this goes. Well, to do that, you just have to go top minus bottom. Sometimes it's just going to be your top minus 0 if that's on your axes. Other times it's going to be another function, but you always go big minus small. Same idea works when you're going left and right. When you're dealing with your y's, it would either be axis of revolution minus y, or y minus axis of revolution for your radius here in the blue, or your height is right minus left. It's what's on the right minus what's on the left. It's big minus small. So here we have a solid shape that we're revolving around the y-axis. So it's a vertical axis of revolution, so that means we have to be dealing with x's. So your bounds are going to be how far left and right your shaded region goes. It goes from 0 over to 1. So that's your bounds. Remember, we need to have our 2 pi in front. Then you have to do your radius. Now, your radius would go from the middle of your shaded region to your axis of revolution. So, therefore, it's going to be this. And so we're going to have x minus our axis of revolution, which is 0. Because remember, your y-axis is x is equal to 0. So it's x minus 0. Well, x minus 0 is still just x. Did not work like I wanted it to. Grabbed the wrong thing, I guess. Then you have your height. Well, your height is what we're dealing with here. Notice it's your function on the top minus down here your axes, which is 0. Well, it's going to be your function minus 0, so it's just your function. And then you're just integrating this. So we still have our bounds. I would go ahead and distribute through. Then I would do my normal integration. So if we do our normal integration, we would get this. Plug in 1 minus what you get when you plug in 0. And so we get 15 or 4 pi over 15. Now, keep in mind when you're dealing with distant shells, you use a slightly different technique, whether you're dealing with x's or y's. With disks, the rectangles are always perpendicular to your axis of revolution, where with shells, they're always parallel to your axis of revolution. So in general, if you're dealing with a vertical axis of revolution and you're dealing with disks or washers, you'd use y's. But with shells, you would use x's. Or horizontal axis of revolution, you would use x's for your disks and washers or y's for your shells. So in general, when you're dealing with your disks and washers, you go pi, your big radius squared minus your inner radius squared integrated with respect to your variable. Now, if it's a disk, you'd be subtracting a 0 squared, so it's really just your big radius squared. When you're dealing with shells, it's 2 pi. The first thing is your radius, which is either your variable minus axis of revolution or axis of revolution minus your variable, and then your height. And your height is always perpendicular to the radius, and that's what you saw when we drew this in right here, that the purple and the red are perpendicular to each other. Now, this chart right here is on the class website, so you can look at it there and use it as a reference.